Okay, electric field outside a charged spherical shell. 1 nanocoulomb. I'm going to write that as a nanocoulomb, just to spite them. I don't even know who them is on this one. Nanocoulomb 1. There we go. Charge is distributed uniformly on a 10 millimeter radius spherical shell, similar to a basketball. That is the world's smallest basketball. What is this? A basketball for ants? Use Gauss's law to determine the electric field produced by this charge at a distance of 15 millimeters from the center of the... Oh, my gee willikers. Blah. We can... Easy. All right. So, we're going to say that Q enclosed over epsilon naught equals E dot dA integral. Simplifying this, Q enclosed is going to be 1 nanocoulomb. We don't care how it's distributed. All we know is that it is inside the Gaussian sphere, and since it's centered on it, it's going to be radiated out uniformly. So we're going to be able to say that E times 4 pi r squared, where r is the 15 millimeters, not the 10 millimeters. We don't care about the 10 millimeters. It could be 5 millimeters. It'd be the same. Same answer. All right. And simplifying this guy a little bit, we're going to then have electric field equals 1 over 4 pi epsilon naught times Q enclosed, which is 1 nanocoulomb, over 4 pi epsilon naught r squared. I put the 4 pi over here because this is then just going to be k, which is 8.99 times 10 to the 9th. And r squared is going to be 15 times 10 to the negative third, quantity squared. Yeah, you can do a calculator. You can do that on your own. That is a low stress evolution right there, and that is all they wanted. They're really tossing out the softballs on this one. Activity 5: electric field inside a charged spherical shell. For the charged spherical shell in activity 4, use Gauss's law to protect the value of the electric field inside the shell, specifically at 5 millimeters from the center of the shell. Okay. Don't know if they had to make a whole new activity just for this. All right. So flux equals Q enclosed over epsilon naught, which equals double integral or surface integral of E dot dA. Draw a little picture here. So this is the 10 millimeters, and we want to look at 5 millimeters. Well, since all the charge is on the surface here, the charge enclosed with this small sphere is going to be 0. Therefore, electric field will be 0, because there is no Q enclosed. Do they ask us to explain? Nope. And I'm not going to bother explaining. Nope. Q enclosed equals 0. So we've already done that problem about 1,000,000 times on the homework. Go watch my videos on the homework. Have you subscribed yet? You should subscribe. You look like the kind of guy who'd be smart enough to subscribe. You see what I did there? Basically made it sound like you'd be dumb for not subscribing. Which you would be, but, you know, not really. Though my feelings would be hurt. Electric field outside of an asymmetrical distribution of charge. When a charge distribution has an irregular shape, shaped like that of a chair or a stapler, is Gauss's law still mathematically valid? In this case, can we use Gauss's law as an effective tool to determine the electric field outside the object? If not, what part of the procedure that we followed above for a symmetrical charge breaks down? Okay, so I'm not going to write these out. I'm going to write it up, but I'm just going to do it all lazy-like. So, is Gauss's law still mathematically valid? Oop. I'm going to do it in red to create this That way it looks like I'm grading their paper here. Still mathematically valid. Yes. Gauss's law is always valid. That's why it's a law. In this case, can we use Gauss's law as an effective tool? We can use Gauss's law, but it will not be an effective tool. If not, what part of the procedure breaks down? Okay. So this is the real part of the question. Zoom in so I get a... Oh, I can just change the brush size? Heck yeah. Ooh, Sharpie marker. Red Sharpie marker. Whoop. Oh my gosh. That is too excessive. Looks like I'm a little child doing this. Q enclosed over epsilon naught. There we go. Close this little window. Yes, I know my Dropbox is synced. Hoop. All right, Q enclosed equals double integral surface E dot dA. There we go. So the problem here with a circle with a chair in it that is charged, the problem here is that it will not send out a radially symmetrical electric flux. So the E dot dA will not provide us a single answer, a single value. What I mean is the theta between this guy. I enjoy the super large brush, but it is getting excessive. So we have an electric field going this way, and sometimes we might have the dA going this way, or vice versa. Idea is that theta between the two will not always be the same. So we can't simplify E dot dA. And that is what breaks down in this case. Okay, I think that's it for this portion. Then we'll move on to the next activity. Thanks.